Welcome to the Empowering Tomorrow's Automotive Software Podcast, brought to you by ETAS, a single source of cutting-edge software and hardware solutions that make automotive embedded systems safe, smart, secure, and sustainable. Each episode, we'll be joined by ETAS and industry experts to discuss how electrification, automation, and connectivity are impacting the automotive industry. Now, sit back and enjoy the discussion.
Hello, everybody. I'm Colin Mundell, your host for ETAS's podcast. I'm a technical business development here at ETAS, and in today's episode, we are going to discuss ground-penetrating radar technology and how it is used in industrial applications, but moving towards the automotive space. Our expert here is Noah Godremus. He is the Vice President of Strategy at GPR. GPR is a ground-penetrating radar company, and ground positioning radar was developed in MIT, and then GPR, the company, was founded in 2017, and in the past 2 years has had a major focus on commercializing and deploying the technology. Noah leads GPR's commercial strategy and partnerships across commercial and OEM businesses. He's developed GPR's technology to localize with centimeter level accuracy in any conditioning by mapping and tracking subterranean data, and has led a team at Continental Automotive that has developed several autonomous vehicles. Noah, would you like to give any remarks?
Yeah, well, thanks for having me on the podcast. I'm looking forward to explaining a little bit about what we do and talk about automated driving in general. Yeah, I've been working in the autonomy space for about the last 9 years now, and have really gotten to see a lot of cool technologies in different spaces, both in the automotive space and in the commercial space. So I hope we can get into some of that.
Awesome, that sounds good. So I've already mentioned ground positioning radar and then also ground penetrating radar. Can you give us a little background on both of these?
Yeah, absolutely. So GPR is the company name, and it stands for ground positioning radar. And we also use a GPR to achieve that. So GPR in a traditional sense is the ground penetrating radar. So that's a radar that typically can penetrate meters through the surface of the ground and create a signature. And these are used for surveying a lot. So detecting pipes and geology and things like this underground. And with our ground positioning radar technology, we use a purpose-built custom ground penetrating radar to create a subterranean map for localizing automated and autonomous vehicles. And the product name for the ground positioning radar is WaveSense. And so I'll be referring to the technology to position automated cars as WaveSense.
Awesome. Thank you for that. How is it used in mobility applications?
Yeah, absolutely. So when you're talking about any kind of automated vehicle, especially in mobility, maybe we'll use like a electric shuttle case, which is a popular case for automated vehicles now. You see things from companies like Cruise or Together, Easy Mile, Navia that have these electric shuttles. They'll follow a predetermined path a lot of times. So almost like a bus route. So maybe you would deploy one on a college campus and it would go from, the sort of drive around the campus with regular stops. And to achieve that in an autonomous fashion, you need localization or way of knowing where that vehicle is on the map relative to its waypoints and other points of interest. And most localization systems in production now for autonomy rely pretty heavily on GPS systems. Sometimes they're supplemented with a LiDAR matching system or a camera matching system. But all of those systems can suffer from different degradations, whether the GPS becomes unavailable or they need another input for reliability. And so the WaveSense system, when applied to an application like that, can create a subterranean map of the subsurface under the route that the shuttle will follow. And then that subsurface map can be tracked to in real time by the shuttle. So for example, if we wanted to map out a college campus, we would take the shuttle that has the ground penetrating radar mounted on it, drive it manually using a remote control around the campus once, and then that map would be ready to be used to guide the vehicle autonomously along with any other vehicles equipped with a WaveSense system. And the matching, what the WaveSense system is doing is it's taking the current scans from the GPR on the automated vehicle, which is seen 3 meters deep beneath the surface of the road, and matching that to that pre-existing map. So that means even if the road gets covered in snow or there's no good landmarks around or GPS goes down, that shuttle can still drive within a centimeter of where it needs to and safely stay sort of on the rails or stay on the path it's designed to drive on. So
Okay.
that's a good mobility case for WaveSense.
Okay. Yeah, that makes sense. So is WaveSense trying to take over the GPS in autonomies, or like kind of use that instead of GPS, or would you also have this in addition to GPS?
Yeah, it will almost always be used in addition to GPS.
Okay.
So GPS has a really it is an incredible technology, or GNSS, we should say, because of all the different constellations that it can be used, not just the GPS, but that will provide a position, and often a very high accurate position, whether an area has been mapped before or not, as long as the antennas have good visibility to satellites. Where GPS becomes challenged is with availability. So a lot of times that it deals with problems like multipath. So multipath is where GPS signals can bounce off of buildings or other structures around the vehicle and adjust the time of flight kind of calculation of the signals. And it's possible for a GPS to give a poor position, but also give a poor position with a high confidence. And that's very dangerous for a functional safety case, because what that means is that it could say with absolute confidence that the autonomous shuttle is at position XY, but really it's not. It's 2 meters off of that position, and it's possible through multipath for it to give you that offset, and you wouldn't know it. It's not a detectable offset. So in those applications, it's really good to have a secondary or redundant localization, something to back up the GPS or to work alongside the GPS and be fused. And so almost all of our applications involve fusion with a GPS or GNSS system. And in some cases, we're doing a very native integration. So we're working with the GNSS companies themselves because they understand where the weaknesses in GNSS come from and the value GPR can bring. They're kind of complementing technologies more so than competing technologies.
Okay. Awesome. Let's switch over to what do you see besides cost, obviously? What are the biggest hurdles and concerns of ground penetrating radar?
One tricky part of getting WaveSense deployed now is there's a reluctance to add any new sensors to automated vehicles as they're trying to get cost out of these vehicles, and that's totally understandable. And so, really getting that WaveSense applied, we have to find a way to reduce some of the overhead of the other systems on the vehicle. So a lot of times these vehicles are using lidars or cameras for localization as well as for object detection. So in some cases, you can reduce the amount of LiDARs that are needed or the amount of compute needed on board these vehicles to reduce the overall cost and sort of offset the cost of adding the WaveSense system. So that's one challenge, is adding another modality. I would say packaging can be a concern as well for certain applications. So the WaveSense sensor, it's called GroundSense. It's typically about the width of the vehicle, 1.6 meters wide, though we also have an 80 centimeter wide sensor. And the sensor is about 3 centimeters thick. So it's not very thick. It's only, a little over an inch thick, and it gets packaged anywhere under the vehicle. And in some applications like the shuttles or anything commercial, whether it's a seaport automated vehicle or a dump truck, it's not a problem at all to package something that size. When you talk about smaller passenger cars, it's a little bit more design and development early on to package something like that. So that's maybe where one of the challenges lie for getting WaveSense deployed. And that's also a big reason too that there's been a lot more interest in the commercial space than the automotive space in the WaveSense recently, just because of packaging is much simpler on a dump truck than it is on a Mercedes S-Class.
Yeah, that makes sense. Do you see ground penetrating radar coming more into play in cities than out in rural areas, because what you said with GPS being pretty confident in their positioning?
Yeah, that's a great question. So the WaveSense technology will work just as well in the city as in a rural environment and so forth. And there's really 2, maybe 3 main reasons that the WaveSense gets applied to a certain technology or a certain automated use case. The first and the biggest by far is availability, right? So availability is we need our localization to work across all of these different challenging scenarios. And one of the biggest ones is adverse weather. So right now, most autonomous vehicles, I don't think there's really many exceptions, probably just 2 or 3 if I can think of any, avoid snow, avoid heavy rain, avoid bad sun conditions by design. And so that's why we see the robo-taxis and the Aurora and torque trucks running, in the southwest of the United States, is they're avoiding adverse weather. So the autonomy applications that need to work in adverse weather, that's where you're going to see the WaveSense applied quite often. The other availability issue is from GNSS denied or complex environments or sparse environments. So the city, like if you tried to drive an automated vehicle through Times Square, GPS will be almost useless because the multipath will be so bad inside that area from bouncing off buildings. But you also have a challenge of a very dynamic environment, which means that if you're using things like cameras and LiDARs and radars, surface radars to try to detect features around the vehicle, so things like maybe telephone poles or the edges of buildings, curbs, lane markings, you're going to constantly have blockage between your sensor and those features because of all the dynamic traffic and pedestrians around the vehicle. The city has availability problems as well. And then when you talk about rural cases, in rural cases, it's the opposite problem, that there's just no features to be had. So if you're trying to operate on, say, a desert road, and you want to use a LiDAR, a radar, or a camera to detect features around the road, around the vehicle to localize, sometimes there just are no features. Another example is like a tunnel. So in a tunnel, it's very homogeneous. Everything looks the same to the surface sensor. So it's very hard to do, to position using your surroundings in something like a tunnel or a parking garage that's very homogeneous. So you'll see the technology get applied both in the city and in the rural cases. I would say, though, that we're really helping the customers that have automated features now or automated vehicles now scale and expand to spaces they weren't able to before. So the city cases, there's very few automated vehicles that operate in the city because of all the complexity and dynamic environment there, not just for localization, but for object detection and prediction as well, that we haven't done as much work in cities, but we have done enough to know that the WaveSense will work, very robustly in Times Square, or we do a lot of testing in Boston where our headquarters is.
Awesome. I guess I see where this could come into play for the automotive and commercial space. Are there any other industries that you guys are targeting for ground penetrating radar?
Let me talk a little bit about the commercial applications.
Okay.
There's some really cool ones. So I spent a lot of time at Continental working on different automotive cases and some sort of outside automotive. So, the mobility stuff with electric shuttles and then long haul trucking and some robotics. But since I've joined GPR, I've learned a lot about these use cases that go back, some of them decades, for autonomy. And the two that I'd like to talk about is mining and seaports. Okay. So maybe seaports first. So when the container ships come into a port, they get unloaded by cranes, and then they have to take the containers and stack these in these gigantic stacks. And then eventually road-going trucks come and move the containers to different distribution centers. So all those operations within the seaport are becoming automated. And some of these ports have been automated for over 10 years. And the way those systems typically work is the cranes are automated so that unload the ships and then load the stackers, unload off of they're called AGVs, and then onto the stacks. There's vehicles called AGVs, which are automated guided vehicles. And these vehicles take the containers from the cranes and drive them to the appropriate stacks. And these are fully autonomous. And the seaport might have hundreds of these AGVs driving around, moving containers. And they have a big challenge of localizing with a really high robustness. And so the main way they localize today is they use they're like RFID chips that are embedded into the concrete. So every few meters, they drill a hole in the concrete of the seaport, install one of these transponders, and then all of the AGVs have antennas to detect the transponders, so they know exactly where they are in the port and they can drive autonomously. And this has been working for about 10 years, but has a couple big drawbacks. One is it's very expensive to install all that infrastructure. It's tens of thousands of these transponders in every port. It's also very hard to scale. They can't add more. It's hard to add more. And then maybe the most important is that technology can only be applied to new ports. So when they're building a new port, it's called a greenfield port. They can apply it. But for ports that already exist that they want to make automated, they can't apply those transponders. And so we partnered with a company called BTG that actually makes those transponder systems. And they're going to actually distribute and sell the GPRs or our WaveSense technology to apply to seaports. So they won't have to add infrastructure anymore. And all of these AGVs, thousands of them around the world, will be able to be guided just using the WaveSense without adding any infrastructure. So that's one really good use case. The mining case is also really interesting. So I was just in South America a few weeks ago visiting some copper mines. And these mines have been automated for decades as well. Both Komatsu and Caterpillar have had large fleets of automated haul trucks. And some of these haul trucks are, 400 tons they can haul at once, or close to 400 tons. So gigantic trucks. And they'll have maybe 100 at one mine. Mine I saw only had about 20 that were automated. But they would drive all the way down into the mine, get loaded by the shovel, and then drive all the way back up and, take the ore to the plant. And to automate these vehicles, they're very heavily reliant on GPS right now. And there's conditions, especially in South America, where there can be sort of solar events called ionospheric scintillations that can cause the GPS to just stop working sort of intermittently. And that brings down the entire fleet. And so in that use case, applying the WaveSense can quickly, keep those fleets running. It can make it faster to deploy new routes, things like that. And so in both those cases, the mining and the seaports, what's interesting is that these are applications that have been running for years and years and years, and they just want to expand it to new areas where maybe they want to go deeper into a mine where the GPS doesn't work, where they want to be able to run it during a scintillation event or during adverse weather. And so we can just apply the WaveSense technology, basically increase what we call the ODD, or operational design domain, that their system can work. And, that's a much easier lift sometimes than trying to be on the, the first, level 4 passenger car, let's say. So that's really been two spaces in the commercial space that we've pursued quite recently and have been quite successful in.
Yeah, it makes sense that you're successful in it, because both of those use cases sound perfect, especially that port one that you were talking about.
Yeah.
Being able to just scan it over real quickly one time and not have to install anything really seems beneficial,
Yeah, exactly.
both on time and money. So that's impressive. So since GPR is a fairly new technology, what have we learned about it, and were there any surprises?
I'll say that, GPR is in ground penetrating radar, goes back to 1950s or even earlier, right? Being used for surveying and detecting pipes, things like this. And really what we do with it, which is really interesting, is we use it for something different, where we're, instead of trying to understand what's underground, meaning, what's the pipes, what's the soil density, what's the infrastructure degradation, all of these aspects that ground penetrating radars traditionally been used for. Instead, we're just using that character-rich data coming off the radar as this fingerprint or this signature that exists nowhere else. And so we can use that as a matching element. And so some of the challenges with that, one big one is that ground penetrating radars, traditionally, they try to have the radar touching the ground. They want it almost dragging on the ground. And the air gap between the radar and the ground can cause issues for some of the signal processing aspects. So we had to get the radar to obviously not be touching the ground. So be mounted, we can go up to about a half a meter off the ground without any real development. And to make that work reliably took a fair amount of development. And it's also not just that simple, because the radar is also moving up and down relative to the ground. So as the vehicle's going over, bumps and jounces and things, that air gap is changing. So that was one challenge, getting that to be robust. The other one is getting the data to be consistent across different collection times. So for example, if you took a standard ground penetrating radar, so if you bought like a survey grade one, and you went and you mapped a road, and then you came back 2 weeks later, right after it rained, and you mapped it again and you tried to compare the data, you see the data is quite different. And the reason is because the moisture that goes into the ground changes the dielectric constant in the ground quite dramatically. And so we had to write signal processing algorithms that aren't necessarily looking at the intensity of the return or just doing a direct match, but instead are extracting the character or the details of the ground penetrating radar data that do not change over time. They're not affected by moisture. And really what kind of features can we create from that subterranean data that will always match across vehicles? And that took years of development to understand that, a lot of data collection, a lot of good understanding. And we have just an incredible team in Boston that really understands this stuff and is able to do that. And then once we have that really character rich data that doesn't change over time, there's the localization or the matching. And the matching has to happen very fast, 10 to 20 milliseconds of processing time to match the current data off the ground penetrating radar to that pre-existing map, and then report back not just a position, but a position and a confidence or a covariance, we call it, of that position. So how accurate do we know our position? And then send that off to the fusion, the localization fusion. So getting all that to happen that fast, it also has to run on a processor that's not cost prohibitive. We have to save that data. There's a lot there on the matching side. So we have some really amazing engineers, do that aspect of it, the matching, the localization portion. So I'd say those are some of the bigger challenges were around the signal processing, getting the antenna smaller. So the first design that came out of MIT was the size of a refrigerator that would go on the front of the vehicle. I think it was over $100,000, the first system. So getting that to, something that you can pick up and carry around, that was a huge achievement by the team too. Ground penetrating radars like to have a big cavity behind them, typically to sort of focus the radar. And we wanted our sensor to be very thin, only an inch thick. And so that was a big challenge. But fortunately, I really believe we have some of the most talented engineers in the industry. Yeah, in that Boston area there, we really have some amazing talent that's able to work on these problems.
That's incredible. I'm guessing you guys take from MIT over there. And,
yeah.
Makes sense.
Our co-founder was from MIT. That's where the tech is from as well.
Okay. Understandable. I guess where do you see this technology going in the future? I would assume trying to make it smaller and faster, right. But anything else?
Yeah, I mean, our kind of future for where we see this going, we're going to take the product where it is pretty much now, which is it's not as optimized to be as small as it can possibly be. It's not as efficient as it can possibly be. But we know we have great use cases now in the seaports, the mining case, some mobility cases. We have an incredible defense application, which is really exciting. And we're going to apply the technology now, and we are. So over the next 6 to 12 months, we'll see these deployed all around the world on different applications. And that will give us a lot more data, which the team needs, give us a lot more growth, and we'll be able to make the sensor even smaller from there, cheaper, more efficient, and we'll be able to apply it to bigger markets, including automotive. So the automotive case is definitely the largest market, and we know we have to get the sensor smaller, cheaper, and one of the biggest, most complex things is the mapping aspect. So localization is only as valuable as what you're localizing, what the map data is you're localizing to. So we can give the position of the vehicle very accurately, but for that position to be useful, there needs to be a map that says what's the environment around that position have, whether it's the road edge, the lane markings, the crosswalks, the stop lines, all of these. And so we're working on ways of taking that GPR map layer and applying it to other HD maps. And that's where this will really gain some momentum in the automotive space, is when we can show that the fleet of WaveSense equipped vehicles can expand the GPR map organically. So crowdsourced, we can take the GPR data, which is very small, by the way. That's very important as well, is that the WaveSense data is very small.
Okay, that was going to be my next question.
Yeah, organically grow to fill out all of the roads, say in the United States, that automated vehicles operate on, and that can become, really an effective tool. And I don't think we're far off from seeing automated vehicles, whether level 2, level 3, or level 4, that can operate in snow-covered roads or in whiteout conditions, or the sun's completely blocking the camera, because they're guided by what's under the road. So that's where we're going with this.
Awesome. Have you guys been working with OEMs yet? Any OEMs yet?
Yeah, absolutely. So there's really two spots where we bring a lot of value to the OEM car business. And the one is what I call the 0 to 1. So 0 to 1 is enabling something that they couldn't enable before. And that's where, to make a level 3 or a level 4 system work, you have to have a really robust redundancy or fallback path. And that's meaning that there's no driver ready to take control. So the vehicle always has to be able to maintain the lane safely or pull over. Even if the car ends up in adverse weather conditions, the GPS systems goes down, the camera gets blocked. In all those cases, you have to maintain the lane. Mm-hmm. So that's where we've gotten the most traction in the OEM space, is we can, applying the WaveSense, you now have a strong redundancy that allows you to allow the driver to disengage, because the car can always maintain the lane, even with these edge case scenarios. Mm-hmm. The other big one is the availability. A couple OEMs have shown interest in wanting their level 2 system, whether it's like a Super Cruise or a Blue Cruise or an Autopilot, one of these, to keep operating even if the road gets covered in snow, or the sun conditions really bad, or it's a rainstorm. So having higher availability of their level 2 system. And again, the WaveSense can be used to keep that vehicle in the lane, even if the weather is really horrible. And as the level 2 market's getting much more competitive, and all the OEMs are coming out with their own versions, having that higher availability than everyone else is an appealing sales prospect. So that's where we've really engaged with the OEMs, but it's been a little bit slower than the commercial space. The commercial space, they really want it now.
It's understandable though too, especially with how big but small your sensors are. I can see how the commercials, they don't really care the size. They just want to get that data immediately and use it. So it makes sense that the commercial space is kicking off faster than the OEMs. But I can definitely see the OEMs purchasing this in the future. So, well, I think that will wrap up what we're talking about now. Noah, thank you so much for joining. Do you have any closing thoughts?
Yeah, I mean, I just, in general, I like to say this. I think this is such an amazing industry that we're working in now, whether it's automotive or just mobility or vehicles, I guess. There's so much innovation now. It just seems to be accelerating more and more the last 10 years. We have these 3 huge macro trends going through automotive now, whether with the electrification, the shared mobility, and the autonomy. It's just an incredible time to work in the industry. And, podcasts like this one are great to, I think, get that information of all of the cool innovations around the world and all the trends. Get that out into sort of the public eye. So I think this is great that you're doing this. And I really appreciate you having me on.
Of course, no problem. Well, this concludes our episode with Noah from GPR. Please check back soon for a new episode, and have a great day.
Thank you for joining this episode of the Empowering Tomorrow's Automotive Software podcast. Please leave a comment or review with your feedback or what you'd like to hear in future episodes. To learn more about automotive embedded systems and ETAS's capabilities, visit our website at ETAS. That's ETAS.com.